Give me a thumbs up. Cool, thank you, Bala. Okay, welcome to the 10th 2020 Argo Workflows and Events community meeting. We started this at the beginning of 2020, and we did that with the goal of kind of talking a lot about what we're doing with Argo Workflows originally, and we've expanded that to include events because we know that a lot of people are using events when they use Argo Workflows. If you've just joined the meeting, it'd be fantastic if you could add yourself to the community meeting document here. It's really good to know where people are coming from and what kind of use cases you guys using Argo Workflows and events for. We need this information so we can make sure that we build in the appropriate software features and we kind of apportion our time appropriately. So it's a small effort from you, but incredibly useful to us. Let me give you just a little bit of an overview of today. We've got a couple of talks here from KubeCon. We're going to be giving a little bit of discussion around the catch-up feature, which Bala is going to do. And then I'm going to show you a couple of the new user interface features coming in to 2.12. That's our plan for today. If you want to ask any questions during the course of today, feel free to just unmute your microphone if you think it's an appropriate time to ask them, or you can drop them into the Slack channel and you can ask them there. And yes, we are recording this. People always ask, are you recording this? And yes, we are. Okay, Clemens, are you ready to take over?
Yes, I am. Hello.
Brilliant. I'll let you share the screen.
All right, let me find the slides. All right, you should be able to see the slides now. Is that the case?
Looks good.
Okay, great, thanks. All right, yeah, hello everyone. So this is going to be a brief presentation on a glimpse at Argo at CERN with a focus on high energy physics analysis workflows, and I'm going to briefly introduce what that actually means. So first of all, a few words about myself. I'm a CERN research physicist working on the CMS experiment at the Large Hadron Collider, LHC, at CERN, Switzerland. So CERN is the European Particle Physics Laboratory. It's in the border region between Switzerland and France. And what I'm doing, let's say, everyday life is analyzing the particle collisions provided by the LHC, recorded by one of the detectors, the particle detectors at this collider ring, which is the CMS detector, and you can see a Lego model here. So this is the biggest particle accelerator that we have on Earth, at least the biggest human-made one. Has a circumference of 27 kilometers or 17 miles, one like that, and it's actually the coolest place on Earth because it's a giant fridge. The magnets need to be cooled down to 1.8 Kelvin, so that's about minus 270 degrees Celsius, or I think I looked it up, minus 460 degrees Fahrenheit. So this is really cold, and it's actually colder than the universe. And we need that in order to bring these magnets into a state with which they are then superconducting and allow us to bend the particle beams around this circle. And I mean, if you look down this tunnel, it's a fairly straight thing. It only bends at the very far end. So we really, this is a huge a huge collider, and it's all underground, about 1 kilometer. All right. So what is high energy physics? It's about trying to understand the smallest building blocks of matter. And I already mentioned the CMS detector. That's a particle detector, which takes up to 40 million photos of the collisions provided by the LHC, and that's per second, and that's happening effectively 24/7, almost all year long. It's not happening at the moment. We're in a shutdown phase, so the last collisions took place at the end of 2018. We're going to restart collisions next year. We can basically we let billions of protons, so really tiny particles, collide head-on, or at least almost head-on, in the center of these detectors. One picture is roughly 2 megabytes, And if you want to store that, this is kind of challenging. So we cannot do that. We can, let's say, get a brief glimpse of that, and then what we can store for further processing on disk is something like 1,000 of those photos, and we call these then events. That's per second. So in total, we were actually looking here at tera to petabytes of data, and we analyze them using C++, Python, or even shell scripts. I mean, we're using them effectively using C++ and Python, and use shell scripts for steering. So this is really a big data analysis. And also the detector isn't small. I mean, you saw the Lego model, but the actual thing is weighs 14,000 tons, has a height of 50 meters, a length of 21 meters, and it's actually a compact version. So even the Atlas detector, which is the one shown here right across, it's actually bigger than CMS. It's lighter though, but we have around 100 million electronic channels. So you can effectively translate that to something like megapixels if you're thinking about a big camera. So we basically take photos with a 100 megapixel camera 40 million times per second. And you can see one of these photos. I mean, it's an illustration here on the right-hand side. And you can see that the collision basically takes place in the center of the detector, and then particle sprays go in all kinds of directions, and we put the detector there to record everything that's happening. And one thing that's often confused, I just want to point it out here. So, I mean, I work at CERN, but the CMS collaboration is actually a collaboration of over 4,000 particle physicists, engineers, computer scientists, and technicians, and students from around 200 institutes and universities from more than 40 countries. And one of these institutes involved is CERN. And we happen to host the Large Hadron Collider and also this experiment. So to give you some idea about the infrastructure, so I mean, analyzing this data is a huge amount of work, and we actually have something that's called the worldwide LHC computing grid that consists of around 170 computer centers. You can see them here on the right-hand side. So the so-called tier 0 is at CERN, so in the CERN IIT Computing Center. And from there, the data after, say, first shot reconstruction of what we've recorded are shipped to several tier 1 sites with high-speed links. They're already distributed all across the world. You can see there's one in the US, one in Canada, and in Korea, and in Germany, Spain, and Taipei, Russia, and so on. From there on, they actually even further then distributed across further tier 2 sites, so around 160. And if I wanted to analyze these data, I actually write my code, and then this code is shipped to the sites where the data are located. And furthermore, there are even smaller local batch farms available, so-called tier 3s. We also have one actually at CERN. It's a slightly bigger tier 3 though. The sites themselves are already often managed using Kubernetes. And at CERN, we have a big batch computing farm. It consists of around 230,000 cores. It's running HT Condor. It's a high throughput computing software, and it's running around 150,000 jobs simultaneously. That's a peak value, and 1.4 million jobs are completed per day. And let's say the standard workflows for the CMX experiment, they're executed using Singularity. So they're not using Docker, but they're using Singularity, but already containerized workflows. Okay, but I actually don't want to talk too much about, say, this, but I want to talk about a different aspect of a high energy physics workflow. So all this, what I've shown you here in the previous slide, is already largely automated. But the challenge, and that's what I spend most of my time on, is using this for the so-called high-level physics analysis. So this is actually then addressing a particular physics question, so that then typically results in a paper publication. And there's a lot of metadata that goes into the physics analysis here. So there are data sets themselves, then of course the implementation of the analysis, and also further data products. There are lots of inputs that one needs to handle and then keep track of, and of course use version control systems for that, so Git. And it's of course also very useful to be able to build some kind of images to preserve the data, because the experiments have been running since 2008, and I mean, this has been quite a few years, and we're basically running a Red Hat Linux derivative. Well, when things started, I think we were on the equivalent of Red Hat Linux 5, which has reached end of life a few years ago, and even the software that we used for 2018 data taking will reach end of life. So Red Hat Linux 6, we call it Scientific Linux CERN edition 6, will reach end of life, I think, the end of next month. So containerization is there in order to make use of the data also long term. Okay, so now when it comes to running the physics analysis itself, what would we have to do? We have to capture the software. So that means we have to know how we can execute the individual analysis stages, and also capture the commands. So how we can then execute this, include all the dependencies. And what I'm particularly interested in, because 1 and 2 are, let's say, somewhat solved, is capturing the workflows. How do you connect the individual analysis steps? And there's, of course, lots of research ongoing already. So several tools are under investigation and partly used by smaller groups. So there's by CERN IT developed a product that's called Rihanna. That's an implementation of the common workflow language. Has a clear high energy physics focus. Then there's, for instance, also Luigi. That's originally been developed by Spotify. There's a HEP-specific add-on that's called Law, and then there's, for instance, also Yadish. I think these languages, these workflow languages, tools won't tell you much. But the question that I asked myself is, can we actually do this cloud native, in particular to reduce overall maintenance and make use of all the nice features that Kubernetes has? And of course, the solution to that are Argo Workflows. So I looked into that a bit more. And just to point out, so the physics analysis I'm talking about starts where the automated workflows currently end. And when you develop a physics analysis, it's done in an iterative way. So the first step, which is a highly parallel step, is actually reducing the data sets to contain only events of interest for the particular analysis using a, let's say, first pass. So I would usually ship my code to one of the grid sites all over the world, say, like, I'm interested in such events, then these events will be, let's say, written out, and I'll then analyze them in subsequent steps, somewhat interactively. So I'll look then into the data and simulation that I selected, and further optimize based on the physics question that I asked myself, and further figures of merit. And then later on, I'll continue down to performing more statistical analysis and optimization. And we'll also have to evaluate dozens of systematic and statistical uncertainties. And once I'm, say, somewhat sure that this is fine, I could, of course, run the whole workflow again, but there are lots of steps where I might actually go back to the previous steps. So I might, for instance, find that my initial selection wasn't good enough, and then I have to run this highly parallel step again. Okay, and just to give you an idea of what this roughly looks like, I implemented in a workflow as an example in Argo. I mean, it's really nice so that one can see this, say, on a single screen. It's somewhat simplified, but I think that the main point here is that it's a delightfully parallel thing. So let me give you some idea of what I'm doing here. So, okay, I create some output directory, and then I want to run on different data sets, both the actual collision data recorded and the simulation that I think is relevant for this. And then I basically ask the database, like, how many data sets, how many files are actually part of this data set. And then I dynamically scatter the workflow to lots of parallel tasks. So this is what you see here. And afterwards, I reduce again this information. So I merge all the parallel jobs based on an individual data set. And then I run further investigation steps. I would, for instance, make a couple of plots. so in figures, and extract a couple of numbers, and I optimize further so that my analysis is really top-notch. And once I'm happy with that, I would go down and continue with further statistic and analysis. And then usually in the end, I end up with a single plot, or let's say a handful of plots that then actually make it to the final paper publication. But of course, I produce actually more than, I mean, I would usually say hundreds or thousands of plots to investigate what I'm doing. And if I'm making, if I find I should go back one step, it's really important that I can move from one step to the other. And I just see a link here at the bottom what this example workflow is based on. And usually there'd be a lot more jobs. So typically I'd run several hundred jobs in parallel in this reduced data set step here. Okay, and just to give you an idea what things could look like. So here in the different colors are the simulation samples that I processed, and then in the black markers here are the data. So this is, let's say, my assumption. So I was looking for a new and unknown physics signal in this toy analysis. And then I perform a fit to the data, and you can see here on the right hand side that the data actually do not support this new physics signal, that if the new theory that I wanted to test actually turned out to be true, the data would support this, but they don't. So my signal gets scaled away almost to zero. And that's important information that I can then feed back, for instance, to the community, and in particular the particle physics theory community. Okay, so before I close, I just wanted to point out what are typical HAP workflow requirements and challenges. So high level of parallelization, something really important. I recently saw that there's been a MapReduce example implemented. So I think that's really useful. So I usually scatter and gather dynamically. That's really cool that this is supported without having to know the number of input files in Argo. Memoization is important. So there are some challenges that come with this when using this at CERN. So we use several custom file systems, for instance, EOS. So I'd have to look into more details and implementing custom sensors for that, so that I avoid rerunning the same step again. And I also need to be able to restart and stop at arbitrary steps in the workflow. And that's also something that's possible in Argo. So that's really nice. Another thing is that we've got the grid, but even though we have several hundreds Kubernetes clusters at CERN, the computing power for typical high energy physics analysis is somewhat insufficient in the cluster, because these clusters aren't shared for physics analysis. So I need to scale out to standard HAP computing platforms. So that means the classical batch system, such as HDConda that I mentioned, and also the grid. And for that, I've recently implemented a custom operator, and I talked about that at KubeCon Europe earlier this year. And that makes it possible to use that. And I think that something that's really great about Argo is that there's this feature to manage arbitrary Kubernetes resources. And if you're interested in how I did that, you can have a look at this talk there. Another challenge is user accounts, so CERN accounts and Kubernetes service accounts. So one needs to have some kind of translation. I recently saw that there's now an integration of DEX for that, but I yet have to look into this and how to use it with single sign-on and OAuth. And I mean, one particular thing is that CERN user accounts come with resources that need to be accessible. For instance, if I run it right out to EOS, I'd have to have secrets that should only be accessible to the user actually running. So there are a couple of things that need to be worked out on the technical side. And of course, then there's a sociological part of it. One needs to train physicists to actually use these new tools and approaches. And I'm planning on developing further tutorials on this. Okay, so that's already the end of my talk. I just wanted to point out that I recently also gave a webinar on using Argo CD at CERN that was more focused at the CERN community. I just link here a slide and the repository and also the recording. So that was again making use of some CERN specific details. So we actually use OpenStack to leverage our Kubernetes clusters. So we can use Barbican for secrets management, and that then makes use of customized SOPs, and there had to be some patches on top of that to make it work. But the feedback that I got, this is not the Argo CD meeting, but I just wanted to say let everyone know that it was highly appreciated that there's this nice web UI, which is, for instance, not there, at least not to my knowledge, in Flux CD. Okay, last thing, this has not been an extensive presentation on the use of Argo workflows at CERN. I only can see a little part of it. There are thousands of people working there. And I know, for instance, some of my colleagues are also using this as part of Kubeflow. So thanks for your attention. I hope this was interesting. And let me know if you have any questions or comments.
A really great presentation of it. Clemens, do you think there's also opportunity to use something like Argo events, maybe to break very large workflows into, a smaller set of more like data-driven workflows or things like that?
Yes, yeah, definitely. I think that this would be a great thing. In particular, let's say, we're producing also new simulation samples or new data coming in, and whenever these data are actually available, one would actually want to trigger a workflow. And I think Argo events would be really useful for that.
Oh, have you seen the new changes made to Argo events recently? It was completely refactored.
I only looked at it briefly, but I actually need to get back to it and look into the details. But I'll do that. Thanks for pointing out.
Thank you very much for that presentation. Really interesting. I've dropped the links from your slides into the Zoom chat, so if people want to go and dig into that information, you can do that now, as well as I'm actually going to take a good look at the Argo CD presentation as well. I'm quite interested in that as well for obvious reasons. Do we have any more questions? Anybody want to? Everybody's loving your presentation in the chat, by the way. You're getting loads of great positive feedback.
Thank you. Yeah, that's very kind.
Okay, great. Okay, so unfortunately, David's had a problem logging into Zoom, so he won't be presenting this week. We'll have him come back in November, and hopefully we can address whatever Zoom issues people seem to be having today by then. So what we're going to do is we're going to move forward, and Bala, who's one of the core engineers on workflows, is going to be doing a short presentation on a catch-up feature. Bala, are you ready to go?
Yes, I'm ready.
Brilliant.
Hi, everybody. I'm Bala from Argo Team Intuit. I'm going to present the the catch-up feature in Argo event. So the Intuit batch team has a use case for the calendar event. So they need to stop and start for some time, but they like to catch up that all the missed schedules between that stop and start period. So that's what we start analyzing the Argo catch-up, the Airflow catch-up feature. We like to similarly support that the Airflow catch-up feature in our Argo event. So we started with the use cases. What are the things we need to support it? So basically, if the calendar event source scheduled for 10 minutes, and if the user is stopped at a calendar event and start after some time, they need to catch up that all the schedules. Sometimes if it is any problem in the cluster, like the node failure or some problem in the cluster or upgrade is happening, so that time all the event source pod will go down. That time that all the duration of the pod is not up, all the schedules will be missed for when it's coming back. So we need to catch up that. So for that one, I enhanced the calendar event spec to provide like the persistence to persist the last successful event in the config map, and the user can define their catch-up functionality. So in the catch-up functionality, the user can enable and disable the catch-up when it's coming back the pod, and the user can define what is the maximum duration they like to catch up. Suppose if the event is down for like a 1 day, but they just want like a last 5 minutes catch up. So they can define like the duration, the max duration here. So for here, I'm going to demo that. I have the same event sources created in my local, and which was running fine. And technically I deleted it. That means it stopped on 9:57. My event is like firing like every minute. So now again, I'm going to start it back, and I have a configuration saying that I want to catch up like last 5 minutes duration. So I'm creating. So what it technically will do that it will go back 5 minutes and find like all the missed schedules and fire it immediately. So if you see that, I can see all the workflows here. If I open one of the workflow, which will be I didn't pass that. My sensor didn't pass the event time. Sorry. So I didn't pass the event time here. But technically, if you pass the event time, you can get the scheduled message, scheduled timestamp in the parameter. And I can show that data equal to event time. Sorry, I missed it. So now I have a sensor which will take a event time as a parameter and process it my workflows. So I'm deleting my calendar event, and I'm updating my persistence to go back as I told that now I'm updating my last successful events in my config map. So I'm just simulating like I'm down for 1 hour to show that how the catch-up event time was passing. 6. So technically, I updated my last event time to that 1 hour before. If I create now, so I don't have any workflow. If I create now, it should fire the 5 events with passing the event time to that workflow. You can see that which was like a 1 minute before, like currently we have like a 34, but 5 minutes before it went, and it has created that events. So this is the way we can enable the catch-up feature to catch up that what are the events are missed in the shutdowning period. Yeah. That's it from my side. Do you guys have any questions? The silence is good. I'll give it back to Alex.
Great stuff. Thank you very much, Bala. So unfortunately, Dave is not going to be able to present today. He's had issues trying to access Zoom, so we're going to reschedule his presentation to November. In the meantime, I wanted to kind of just talk a little bit about version 2.12. So I'm just going to share my screen with you, so we can talk about that. Now, version 2.11 and 2.12 have had quite a number of changes that are very much under the hood changes. One of our goals is to kind of really reliably run very large workflows. And so by reliably, I mean that we want to be able to run workflows, even if Kubernetes decides to do things like delete your pod underneath your, there's some kind of transient network error. And by very large workflows, we're talking workflows with nodes in the ranges of 10 to 20 to 30,000 nodes. We can't actually go much bigger than that, because there's actually a limit in Kubernetes to how many pods you can actually run at the same time. So most of those changes are kind of under the hood at the moment. So I'm mostly going to be talking about kind of two aspects about version 2.12. I'm going to give you a short demo of some of the new reporting orientated features that are in it, and I'm going to give you a short, just a short tutorial about how those work. And then I talk a little bit about what's coming up after version 2.12. Okay, so obviously you guys are probably familiar with the user interface here. I've been running some large workflows. I'm going to point out some new details in the user interface here to you as well. So the first detail here is that we now have a new column in the workflow list. And actually, if you go into a particular workflow, that same information is shown in the workflow details page. It'll show you the progress of the workflow. The progress is calculated as the number of nodes in your workflow that are completed over the number of nodes that need to be run. This can actually change at runtime because we don't know when we start your workflow the number of nodes that it might contain. So for example, you might have a single step that runs, then has a with item step or a with sequence that runs a number of steps, and it might initially say that it's, for example, 0.1 complete, and then suddenly change to being 1 of 251 complete, and that'll be displayed in the user interface, and you can kind of see that progress. That's going to be useful to be able to understand, is my workflow progressing as I expect it. The second feature we're adding, and I'm just going to demonstrate this now, is the ability to kind of see the progress of the workflow. That one's a bit too quick, so let's see if I can start another one up. To see the progress of a workflow, you do need one that takes more than about a second to complete. So, okay, I don't know if you caught it there, but this workflow only runs 4 seconds, and there's a little progress bar that will appear in the duration column that is based on an estimate of how long that progress takes. That progress estimate is a bit coarse. It's essentially how long did the last workflow trigger from the same template, same cron workflow template, or the same workflow template take. If your workflow has a variable fan in and fan out, then that number can change quite a bit. So for example, if sometimes you run 100 nodes and sometimes you run 50 nodes, that obviously the runtime of those two workflows will be different, and the estimate won't be that useful. But if your workflows are quite similar, that estimate will be reasonably accurate. I'm just going to resubmit this one. I'm going to stop this immediately because it's a relatively large workflow to run on your laptop. When this runs, and this should show you a bit more clearly the kind of information that you will get when you run this, if it's going to start. Here we go. So you get a progress meter in the main node here. You'll see that this duration meter kind of ticks up here, and you can see that the progress currently shows me of different numbers depending on where it's got to in the progress of this. Okay, I'm going to delete this one because it'll be enough to slow my computer right down if I leave it running. Hopefully, it hasn't caused any problems already. So while it's loading, there's a new page here that appears on the left-hand side. And this is called Workflow Reports. This is kind of a new feature. I can go into here and I can choose a pre-existing workflow template. And this will then load up a graph of that template, and it'll provide me information about the average runtime of recent executions. It'll show me a graph of those executions as well. And it'll also show me the amount of CPU memory, and if you've got GPU or other kind of resource, it'll show those in the graph. The use case for this particular page is, is my workflow taking longer? Is my pipeline taking longer? Is it consuming more resources? When did it start consuming more resources, and when did it start taking longer? Help you analyze those situations where you've got a problem and kind of narrow it down perhaps to a particular change, or just get a general idea if a workflow is expensive or not. So these are the main additions to V212. We're also going to be introducing RBAC for SSO. So if you're using SSO today, you'll know that RBAC automatically, if you can log in through using SSO, the service account that it'll use will be the Argo server service account. That's not very flexible if you want to have different users to have different service accounts with different permissions. So the most common configuration for SSO today would be to set up just as read-only, so people can see everything. RBAC with SSO allows you to configure different service accounts to be used by different users, and it's a rules-based system. So essentially, the service account that's chosen to be used for a particular user is based on the user's subject, and probably more usefully their OIDC groups, or OAuth2 groups, assuming your OAuth provider supports it, which some don't, but many do. And you can set up rules, for example, saying if I'm in this group, I get to use this account, but if I'm in another group, I only get to use a read-only account to give you that subtlety permissions. Version 2.12 is likely to be the last in the V2 lineage. In the next quarter, we're planning to move to V3, not necessarily because we will introduce large numbers of breaking changes. This is kind of forced on us because of the way that Golang does Go modules. You can't actually migrate successfully to Go modules unless you increase your major version, because Go kind of mandates it's not great. Most other languages don't require you to do that, and unfortunately, it's going to be forced on us. And as part of that work, we are going to be changing the user interface for Argo Workflows to make it a separate deployable unit that will allow us to build in new features and capabilities into the user interface. Initially, we're planning to provide some new views related to Argo events to allow you to view different types of events in the user interface, and also your configuration, and understand a bit about why did my workflow trigger? What was the cause behind that trigger? And that will be coming up soon. We may add other additional information into the user interface. If you want to find out more about V212, there's a blog post that just talks a little bit about that. And obviously, you can go into GitHub, or you can click on to the milestones tab and see what particular pull requests and issues are assigned to V212. This is one of our largest releases, and I think it may even have the highest number of pull requests and the highest number of contributors. We typically get 20 to 30 contributors to each release. This V212 has actually had 41 different contributors, and I suspect that actually might be higher since this blog post was written a week ago, because we're still adding pull requests. I know that one of the questions you're going to ask, we always get, is when is 2.12 going to drop? I'm hoping it'll drop within the next 2 weeks, so 2.12.0, and then we'll plan to probably support that for a longer period of time than other releases, because people tend to not migrate from a V2 to a V3, even though we're going to try very hard to make that migration almost seamless for the majority of users. There's always kind of a reticence of people to migrate, so we will be back putting bug fixes and so forth from a V3 to V2. Okay, that is all I wanted to show you about V212. Are there any questions any of you would like to ask, or any commentary? Great stuff. I like it when there's no comments. Great stuff. Okay, so we'll draw our meeting to a close just on time, which is quite nice as well. And if you do want to come and chat about any of the upcoming features in Argo Workflows and Argo Events, or any questions you have, obviously come and join us in the Slack channel. If you've got any presentations or materials you want to share, it's always fantastic to have people come along and present at these meetings. So kind of DM me on the Slack. We'd love to have you come and present, or even work with us on blog posts talking about the stuff that you're doing. We do really love that. And I will let you get on with your day. Have a wonderful day, everyone.
Great. Thank you for all the presentations.
Thank you. Bye-bye.
Thank you, guys. Bye.